Alright, so today I'm going to be going over like a summary of what I really know about classical mechanics. Hopefully I won't be really using too much math because that's not really my strong suit in physics. And yeah, you guys can just enjoy this. Alright, so the first thing we're doing is speed, velocity, and acceleration, and how they're different and stuff. So to start right off, speed is practically just a rate of change. It's like the formula you're seeing on screen describes it pretty well. It's got distance divided by time, which practically shows you the rate of change. Well, velocity, on the other hand, believe it or not, is practically just a rate of motion or change in a specific direction. So like while speed may have a magnitude, it does not have a specific direction. So with velocity, it has a magnitude and a specific direction, and we call that vector quantity. Acceleration is the rate in which, the speed or the velocity would change. This could be, speeding up, slowing down, changing direction, etc. You could tell if you're like in a uniform acceleration, like, steadily changing direction, slow down, or speeding up, or like a sudden stop, or sudden, speed up by how the graph is, how wonky it is. Alright, so moving on from speed, velocity, and acceleration, we'll go on to mass and weight. So mass is practically, the amount of a thing or material is in the object. This can equivalent to how hard it is to move, which we call inertia, and how much gravity it gives out. Weight, on the other hand, is, how much, the mass would give or experience from gravity. Moving on from mass and weight, we'll go to force and momentum. So a force is basically an effect that would either change, the object's velocity or momentum. So we would measure a force in a newtons. So for example, we'll just take from the picture there, a frictional force is, say for example, you're riding your bike. There would be friction on the ground and the tyres riding the bike, stopping it probably a large amount. And say you were to hit those brakes, there would also be another friction in like the spring locks or something in it. Or just stopping the thing completely. Alright, so momentum is the outcome of the object affected by the force. It shows, like how hard it is to stop it, I'm sure you guys may have heard of P equals M times velocity. This, just, it's pretty obvious in itself. Momentum, it's also always conserved. We call this conservation of momentum, I'm sure. This would mean that, the momenta, which is just like, the quantity of the momentum in the object, would always stay the same. Before and after objects would interact with each other. A good example of the conservation of momentum would be, so when you're playing, pool ball, you would say hit the ball and it would crash into all the other balls. The ball, the original ball, which smashes into the triangle of balls, transfers all of its momentum to all the other balls, scattering them around. And then the original ball would stop dead in its tracks. Next off, we'll be talking about Newton's 3 laws. So for law number 1, we would have, an object would, either be staying still or would be, in a constant, uniform, steady movement, until a force would act on it. An example I used in another video was, with a football. Say you kicked a football and you didn't have gravity or air resistance and all those forces acting on it, it would go in a straight line up in the air and would stay that way until a force acts on it. And say you didn't even kick the ball in the first place, it would practically just stay there forever until something acts on it. Newton's third law is, the world famous equation F equal ma. What this means is, it's pretty obvious. Force equals mass times acceleration. That means, say you slam into a wall, the force in which you slam into that wall would equal to your mass times the acceleration in which you slammed into the wall. To prove this, we would, say, put the Olympian runner that weighs 70 kilograms, a regular runner that, say, weighs, 70 kilograms as well. Say the Olympian runner will run 10 meters per second, and the regular runner runs 5 meters per second. They both slam into the wall, or the Olympian runner would, slam to the wall harder with more force because it's faster. Well, for Newton's third law, I think we've actually got a pretty good picture here. So what's happening here is that the balls slam into each other with say 10 newtons per second force, probably a lot less, but those balls slam into each other, you have the equal opposite force pushes the other ball up, and then that keeps going on and on and on until something affects it. Well, back to the third law, we have, for every force, we have an equal opposite force on it. Yeah, you probably don't even need me to explain that. So the next one we have is work, energy, and power. This is probably going to be a very quick one, so just to sum it up. So work is while, a force doing its thing. Energy is practically, the capacity for, how much you could work. And power is, how long you can work. How good, how long, how strong. It's a quick one. Next on the list, we have potential and kinetic energy. So to start off, we'll just start off with potential energy. So practically, potential energy is, the energy it has in which a force moves it or, changes it and stuff. But usually we would only talk about this in, potentially, gravitational potential energy and such. That would usually depend on which the height you're on Earth, less gravity is affecting you. So the further an object falls, the more potential energy it has, for obvious reasons. Also, another thing to note with the formula we have there, PE equal mgh, which is practically just potential energy equals, mass times, gravitation due to acceleration times height. We've already explained that height is an important factor, so is gravity. But another thing to note is that the more mass you have, the more potential energy you also have. Moving on with kinetic energy. So, despite its formula, it's actually pretty simple. It's just, the energy in a moving object. So, potential energy and kinetic energy actually have a relation. So I think a good example is on a roller coaster. So, when you go down that slope, the potential energy in the roller coaster turns into kinetic energy to power the roller coaster going down. I think that's a good example of the relationship between those two. Alright, so going on to practically, gravitation, gravity, and all that, yeah. So right now in front of me we have universal gravitation law. F1 equals F2 equals G times M1 times M2 divided by R squared. So what this basically means is, so you've got, G, which would be, universal gravitation acceleration, which is 9.81 meters. And then, so mass 1, mass 2. So you see the little circle, they exert a force towards each other. The distance squared would divide that force. this meaning that distance squared, dividing into the two masses and forces, exerting the object, would give the two gravitational fields between the two. Anyway, that's really all I know about classical mechanics. Bye.